Hello, Nicole. I figured out the VPN thing, so I'm just making some final changes to that. And I'll show you one more time, and I guarantee you it'll work because I've done it from 3 or 4 different computers now. I'm gonna see if I can change everybody's password by default or change the parameter real quick.
What's happening? I'm a savage.
What was that? Who's here that wants to try? You want to try it? I'm gonna have to change the passwords one at a time here on these to make it so that it doesn't expire. And then you change your password once you log into a desktop. So who wants to try this VPN thing right now with me?
I'll try.
You want to try it, Franklin? Okay, so let's see, Franklin and Juno. So we'll try it with Franklin. If this works, then that's how we'll do it with everybody. Who else wants to try it? Who has a Windows computer? We'll get it working with Microsoft. I mean, with Apple, but I want to make sure that it works with Windows. Do you want to try it, Nicole? Do you have a Windows computer? And Sreya,
I have a Mac computer.
Okay. Could you figure out where in the Mac to set up a VPN connection?
I did. I sent you an email with some screenshots of where I got stuck.
You're right, I saw those. And I think I figured out what we need to do. It's just 1 or 2 little minor things.
Perfect.
Reset Sreya. Quick, and then I'll reset yours. Nicole. Just give me one more sec here. Oh, here it is. I can't do it. Okay. Good. 1 sec. I can reset these passwords on everybody with 1 swoop. Should be able to. see if that saved that info. It did not. Why not? Sorry, I wasn't quite ready for the class. I've been working on this kind of most of the day, messing around with it. Okay. So let me share you my screen and let me show you just a couple of minor little things on the VPN, and then I'll continue with chapter 5 here today. But I want to, and this is not critical for the exam 1, but this is hopefully something that we can get going so you guys can start doing some of the homework assignments this weekend. So I'm not plugged into my external screen, so I'll just share my primary screen here on this laptop. Okay, can you guys all see my screen?
Yes.
Okay. I'll pull out my chat window so I can see that. Okay, so I'm going to click down here on Network and Sharing Center. Again, this is how you do it on a PC, and it's, Nicole, you're going to have to help me with this on a Mac. I'm going to go to Change Adapter Settings. I've already got one set up, so again, I'm going to go ahead and just delete this one, and then we'll create a new one so we can create it from scratch. One that we know works. Go back here, set up a new connection, connect to a workplace using my internet VPN connection. Internet address 192.138.194.45. Destination name, I'm going to call it, excuse me, EI Lab VPN. You can leave that check marked if you want. Actually, no, let's turn that off because you're going to end up changing your password once you've gotten logged in the first time. So click Create. It's created it. I don't yet want to connect to it. Now I want to change adapter settings. There it is there. And I want to right click and change its properties. That's all fine there. Go to Options. Change that idle timeout to something appropriate, but I'm going to put it on 30 minutes. Otherwise, if you leave your computer on and you walk away, then it stays logged in all the time. You don't always want to be logged into the EI Lab. Okay, here was the stuff we needed to change. Security, change that to L2TP. We already knew that before. Advanced settings, go there. Change pre-shared key to the DISC 2020. Disk 2020, which is the info I had given before. Nothing's different yet. Change data encryption here from optional encryption. This is what we got to do to required excuse me, encryption. That's because I told my firewall to require encryption. You never want to use VPN without encrypting the data coming out of your computer and going back into the server. Furthermore, the next thing we want to do is down here where it says allow these protocols, tick that little button there. Okay, once you tick that button, then we can use these protocols. We don't want that unencrypted version, but we want to enable that one, CHAP, and then also MS CHAP. Now, Nicole, you may not have the MS CHAP because that's a Microsoft thing, but you certainly should have CHAP. Somewhere on your VPN connection, Nicole, you should be able to click on CHAP, Challenge Handshake Authentication Protocol. All right, and then you shouldn't have to change anything on networking. You shouldn't have to change anything on sharing. So that was the difference. Required encryption, allow these protocols, CHAP and MS2 CHAP. Don't uncheck that if it got checked for whatever reason. do not allow PAP. Okay, so I'm gonna click on that.
Sorry again, and it's that 192.138.194.45, correct?
Right, here, I'll type it in the chat window, 192.138.194.45. And the PSK, the pre-shared key, was disk 2020. I'm gonna click here and I'm gonna click connect. It's asking me for my username, which is the student ID. 1, 2, 3, 4, 5, 6, 7. I set up a test student ID with all zeros and a 1. And then the password, again, is that generic password for everybody, which you're going to change later on. So that's the generic password for everybody. Oh, I'm sorry. Well, wait a minute. Certificate. It didn't save my changes. That's strange. DISC. It didn't save my when I put in DISC 2020 there. It just worked on my other computer next to me, so I know that this is working properly. 1, 2, 3, 4, 5, 6, 7. Connecting and now completing. I wonder if that's a bug in Windows, because I definitely typed in that disk 2020 and clicked save. The same problem you have an error about the certificate? Yeah, I'll bet you that's a bug in the Windows VPN setup, that you have to go back in to the settings and type in that disk 2020. Now, it sits here for a long time. It says completing the connection for a long time, but I believe it's already complete. If I try to go to ipmonkey.com, I'm now getting 192.138.194.45. So were you able to get it working, Nicole or Franklin?
Negative. I get that. Yeah, it just says that the authentication method is not the right username or password, does not match.
Okay, let me double check. So it's Franklin.
I still haven't been able to get it figured out either. I can't even find the CHAP function for the
What
VPN.
I may do with you, Nicole, if you don't mind, after I'm done with the class today, can we do like a team viewer session, and so you can show me your screen and maybe I can see what you're doing?
That
would
works.
be very helpful, and then we can share that with the Mac people. Reset password. Okay, so Franklin, you want to try it again? Make sure that you're putting in this BMJ all uppercase and then lowercase US3R exclamation point. And you're using your student ID as your user ID, right? Starting with 197. I think I need to reset yours, George.
Yeah, it says please contact the administrator of the RAS server, notify him of this.
Okay, 1 second. You're using a Windows PC?
Yes, sir, I am.
Okay. Okay, you want to try it one more time for me? And in the meantime, let me compare what's the difference between my account and your account. Remember, Zen admins, VPN authorized users, and domain users. Remember, should work. Is it working for you now, George or Franklin?
Negative. Now I have the error that says that the selected authentication protocol is not permitted.
Why don't you just try only selecting chat, MS chat. Go back to the settings. In other words, let's go back to the settings for the VPN. I'm sorry, this is so much trouble. This is should not be that much trouble. Properties, security. Take off that checkbox and just use MS Chat only. Make sure that that's not ticked. Make sure allow these protocols is ticked. Excuse me. Require encryption. Disconnect if server declines, and it's L2TP with the pre-shared key there. I want to disconnect and reconnect. Actually, I'm going to try, you know what? Let me try it with somebody else's. Let me try it with yours, Shreya, okay? I know what your user ID is, so I'm going to try it with yours real quick. Sure. Okay. Let's see. I'm going to stop sharing for just a minute because I don't want you guys to see her user ID. The connection was prevented because of a policy configured. Okay, so, all right. Okay, so it has to do with what we've determined. It has to do with the user settings in the domain controller. All right, I can fix that, but let me fix that after class. So at least I've figured out the VPN part with the user IDs that I've set up. I should have tried somebody else's. Okay. All right, let's finish up chapter 5 today then, okay? And then I'll talk about what's going to be on exam 1. I'm going to make it available starting tomorrow morning. I'm going to change it up, so I'm going to make it a little simpler, if you know what I mean, for the summer. Make it take some of the things off that we really didn't get to yet. Chapter 5 is in here somewhere. I downloaded it yesterday. I just downloaded it again.
When will the test be due?
Probably I'll make it due Monday at midnight. That way you guys have all this weekend. Think that's going to work for you? I might go even longer than that on it. There it is. It says I've downloaded already. Don't know. I couldn't find it. I need to clean up that downloads folder. Okay. We were right about here, and we talked about, and what I had mentioned was important was I wanted you to remember or memorize or be able to tell me what these well-known services are and what ports they're related to. And again, these are layer 4 addresses. So if I ask you on a test, by the way, on the first exam, give me an example of a layer 4 address, you're going to tell me port 80, port 443, port 21. An example of a protocol at that address would be not HTTP or FTP. An example of a protocol at layer 4 is simply going to be TCP or UDP. Again, there's really only 2 protocols at layer 4 that we use. TCP, which is Transmission Control Protocol. This is the session-oriented protocol where every single packet and segment needs to be received, sent and received, like in the case of an email or a file. And then UDP, which is for streaming audio and video, so Netflix and Zoom and things like that. At layer 5, examples of these things that we see here, HTTP, FTP, those are all layer 5, application layer sample protocols, okay? Transport layer functions. So as I mentioned before, that magical 1460 byte maximum, that's because the TCP header adds 20 bytes and IP version 4, layer 3, adds 20 bytes. Within this 20 bytes is the source and destination IP addresses, and within this header, among other things, is the source and destination port number. Now, as I mentioned before, the destination port number is really the only one that we're that much concerned with, because the source port number is a number that your computer randomly grabs out of its pool of numbers to use temporarily. Usually it's something over 1024. It looks to see, am I using this particular channel? No, let me start using this channel. So it takes the 1024 channel and puts that in as the source channel. The destination channel is defined by the application. So that's defined by Chrome or an email program or whatever you're using. So that's going to always be the important one, the destination port number, port 80 in the case of surfing the web. The only reason we need to have a source port number is so that the server, when it sends a message back, it's using that port number to send the message back to you. So the destination port number there is whatever port number you gave it originally. So the transport layer, one of the major functions is segmenting, which means breaking it up into smaller pieces. And as I've mentioned before, the reason that's important is because you are on a shared network. The internet is a shared network. If you make your packets, if you make your frames, if you make your segments too big, several things happen. First of all, the packets don't interleave well. The segments don't interleave well on the internet. The internet is kind of like a bunch of one-lane highways. If you're on a one-lane highway, or let's say it's a two-lane highway, and you're driving a nice fast car, there's maybe only two of you, that's a small packet, and you come up to a dump truck or a semi-trailer truck driving slowly on the road, and you want to get around it. First of all, it's hard to get around it, probably not going as fast as you, can't speed up and slow down as fast as you. In other words, large packets or large delivery vehicles are unwieldy and difficult to deal with on the internet. Now, they're not really vehicles, okay? It's just a stream of ones and zeros. But because of that concept, that virtual concept there, we want to make our packets not too big. So we break them up into little pieces. If you've got a delivery that needs to go from point A to point Z and it's bigger than can fit in one 1,500 byte packet or bigger than can fit in one truck, you break it down into a bunch of smaller trucks and number those trucks 1 through Z or 1 through whatever they happen to be. Conversely, you don't want to make your frames too little because then you add a lot of overhead. If every packet and every segment and every frame has additional overhead, you're adding 20 bytes here, 20 bytes here, and another 16 to 20 bytes for Ethernet on top of that data stream. So you don't want to make them too small, just like your car. You don't want your car to be too small. If you've got some friends you want to take somewhere, 3 or 4 of your friends, and one of your friends says, well, you know, I drive a Miata. Well, it's a little two-seater. It'd be difficult to fit 3 or 4 people in there, so it's not appropriate for delivering a family. Somebody else might say in your group, well, I've got a van. Let's all go get in my minivan and we can drive to wherever we need to drive. That's more appropriate. If another one of your friends says, well, I've got a semi-trailer truck or a box van, and you can all pile into the back of that, well, that's not maybe appropriate. It's too big. You don't need an RV to take 3 or 4 people somewhere, okay? So the other reason that's important to keep the frame sizes of the packet and the segment sizes small, particularly for the internet, is because errors do occur. And I spoke about that in the data link layer chapter, and I know I need to upload the second half of that, the data link layer chapter. I haven't recorded it yet, but I'll record it after this. And I promise to do that tonight because I've devoted all day today to just this class. If an error occurs, and errors occur, and if I can just talk about layer 2 real quick, the data link layer, one of its jobs is to figure out if errors occur. Now, I'm talking about errors that occur in the physical layer, layer 1, presuming that the data that's leaving your computer is accurate and the data that's coming into your computer is possibly accurate. The only thing that really causes the errors, and I'm not talking about application layer errors, I'm not talking about you typed in the wrong address or somebody made a mistake somewhere. I'm talking about errors that are caused by lightning, by interference, by magnetic interference, or some other sort of interference that is causing the zeros in the data transmission to be turned into ones. The data link layer's responsibility is to correct those errors. Now, the way that errors are corrected is they're not really corrected. The data link layer of the receiving computer, it does a little mathematical equation on that stream of bits that it got. And if it does not get the appropriate answer, let's say, for example, it's very easy checking. It takes the number of ones that are in this data stream. There's ones and zeros. And if the parity checking is on, it might say, okay, I expect to have an even number of ones here. Did I get an even number of ones? No. Well, then that means one of the ones might have flipped into a 0. The receiving computer creates a small layer 2 data link frame that goes back to the receiver that says, hey, that frame you just sent me a second ago, it's got an error in it. Can you send it to me again? So errors are not really corrected in most cases with networking. A retransmission request is put out there. So at the data link layer, your data link layer of your computer says to the device that sent it the frame, hey, I didn't get it all, or I didn't get what I was supposed to have gotten. Please send it to me again. And this is happening at layer 2, this is happening at every single hop. And when I say hop, I'm talking about the physical devices that you're connected to. So between you and your gateway at home, probably sitting on your desk next to your laptop or near it, or in a closet near you, there is a communication going on at layer 2, and there may be some retransmission. And then between your internet modem and your internet provider's equipment that it's connected to, which might be in the neighborhood or a mile away or a couple of miles away, there might be an error that occurs there. And then between the internet service provider's equipment in Houston here and whatever other internet service providers involved that you're sending your data to, there could be an error between them two. So errors can occur at many different levels, even if you've got the best internet connection between your laptop and your modem, like you're hardwired, you're not using Wi-Fi. An error is likely to occur with, 1 out of every few hundred frames. So if we made our frames too big, if we made our frames 10,000 bytes, that takes time for a computer to regenerate and retransmit those 10,000 frames. It's kind of like putting up, if you want to think of a better analogy, think about balloons that you're putting up in the air, and each one of those balloons has a piece of your message tied to it. You're sending a message into the ether. Did anybody look up ether, by the way, to see what Ethernet was? Let me open my chat window. I'll post those tonight, Nicole, I promise. So what did, Stacy, what did Ethernet, what is ether? It goes back to like the 19th century. What is ether? It's a gas. Do you have a microphone? Can you turn it on and talk, Stacy?
Yes, I looked it up the other day when you said it, and now I've forgotten, but it was kind of like the ether, that there was a theory that things pass through this ether that's all around us, like in the air or something to that effect, kind of. I'm not sure.
Yeah, you're close. You're close. There was a theory by historical scientists that said that the Earth and everything outside of our atmosphere it was floating around in a special gas called ether, because we didn't know about air and oxygen and nitrogen in space. And we assumed, as a matter of fact, if anybody's ever watched any of the old, and I don't expect anybody to have, but if you watch any of the old videos of Buck Rogers, and not the Buck Rogers from the 70s with Gil Gerard, I'm talking about the Buck Rogers from the 30s, really old science fiction movies. When they show spaceships flying from here to Mars, the air is gray or blue even. They did not realize, because we hadn't been to space yet, they didn't realize that once you get out of our atmosphere, everything's black, because there ain't nothing out there. So the point is that they used this term, this historical term ether, meaning this mysterious non-fake gas that we believed was out there in space, that everything was floating in, to mean Ethernet. So when somebody says it's in the ether, they're talking about they floated up an idea and it's floating around and people are thinking about, is this a good idea or not? So back to our situation where, why do we have such small packets and segments and frames? In the case of a segment, it's only 1,460 bytes. If we allowed our frames to be much larger, that's like a large balloon. So if you take the analogy of using your writing a letter. Let's just say you wrote a letter. It's several pages long. You take each page of that letter and you tie it to a helium balloon, and you float that helium balloon up into the ether, and eventually that helium balloon will go be delivered or be found by whoever it's supposed to be found by. If you decide, well, I want to take all, if you want to put in multiple pages, let's say you want to send the Bible somewhere, it's got several thousand pages in it. If you wanted to put that all in one balloon, you're going to have to use one big balloon, 20-foot in diameter balloon, because the Bible's heavier than one page. And I'm not trying to be religious. I'm just using that as an example, because everybody knows the Bible's a thick book, or the dictionary. How about that? So if you put a big balloon up in space or up in the ether, what are the chances of that big balloon getting having something happen to it? Much greater, because it's a bigger target. That's my point. A bird could fly into a big balloon. I could shoot down, if I was a bad guy, I could shoot down a big balloon because it's a nice giant target in the air. It'd be much harder to shoot down a smaller balloon. So not only does it take longer to regenerate, to fill up another giant balloon, then I have to regenerate that whole Bible again. I have to pull all of my copy of it out again, attach that one to this giant balloon. It's a big target. So the larger that frames are, the larger that segments are, the more likely that your frame or your segment's going to be affected by some sort of interference. Okay, do we all understand that concept? That's why they're small. Why did we decide on 1500 byte frames? That came about through years of just experimenting with frame sizes. Now you can, some switches that you buy will let you increase the size of the frame up to 10,000 bytes. It's called super frames. And what that does is it basically reduces your overhead here. You can have up to 10,000 byte super frames. But that only works between two pieces of equipment that know what super frames are. Your little laptops doesn't do super frames. There's no super frames capability, so it wouldn't make much of a difference. But if you had two servers and they were in a data center and they had high-end networking cards in them, and you could enable super frames on those two servers, and they're attached with a switch and they're literally right next to each other, the likelihood of having a data link error or a physical layer error is very unlikely or very low. So let's go ahead and allow big giant balloons to be used, because they're probably not going to get shut down in a very safe, short environment where the ether is literally just a few feet. Okay, so that goes back basically to the data link chapter, but it's all tied together. Now, in some protocols, by the way, the bytes are only 53 byte maximum packet sizes, like in the case of ATM or DSL. And that's because those networks are shared even more. So it's only 1,500 bytes on Ethernet. It's only 1,460 bytes if you're using Ethernet underneath. If you're using something else like ATM or DSL, it might be 53 bytes. It has much higher, or cable, even cable modem service. Cable modem service is not Ethernet. If I could just break away for 1 minute from this. And this is going to be in the thing I'm going to upload, but I'm going to go ahead and mention it now because I want you to look it up. That is a cable modem specification. It is not Ethernet. It looks a little bit like Ethernet if you were to open up the frames and look at them. And those are frames because it's layer 2. Okay, the frame sizes are much smaller because DOCSIS, like DSL. Does anybody have DSL in here, by the way? That's AT&T's old school copper service. I think the maximum on it in Houston is only 20 megabit per second, unless you're using fiber. Hopefully none of you, Stacy, are you saying yes to DSL? So you're on DSL or not? If you are, I feel sorry for you. Okay, no to DSL, yeah. There are still a few companies in town, or a few customers, a few end users in town that are still on DSL because they just haven't bothered to upgrade 20 megabits per second fast enough, like your grandparents, for example. Those, in the case of DSL, it's only 53 bytes. And again, that's because the service is usually a lot slower, okay? If it's a really fast service, like it's fiber optic speed, you can do Ethernet over fiber optic because it's nearly the speed of your, it can be the speed of your Ethernet. The slowest speed Ethernet, by the way, is 10 megabit per second. Most of you are operating on a network inside your house on a 1G network or gigabit. That's 1,000 megabit per second. The cheapest network cards you can buy will do 1,000 megabits per second. So 1500 byte frames are fine. But most people's internet connections are, 100 megabit or slower, especially uploading. Now, for those of you that think you've got really super fast internet speed, does anybody in here have gigabit or 500 megabit or something that they consider really fast? Because they got a good deal from you. So you've got gigabit. I'll bet it's not gigabit in both directions. I'll bet
No, it's not.
I'll bet it's asymmetrical. In other words, you might get gigabit down, but you probably only have like 10 megabit up, or maybe 20 megabit up. So they call it 1,000 over 10 or 1,000 over 20, which is okay for most of us. That's okay because what are you doing most of the time? You're downloading. You're not uploading a lot. You're downloading. You're watching videos. So when you are uploading, things are a little bit slower, but that's okay. So back to the transport layer here.
Yeah, I have 195 upload right now.
195, that's pretty good actually. But you're probably paying quite a bit more than the average person for your internet service.
I just pay $100 a month, so.
That's pretty good. Is that through AT&T?
No, it's through Consolidated. They got fiber optic down here. So.
Okay, so you are probably in either an apartment complex or a neighborhood that has a special deal where they can offer you that, but it's not common in a lot of areas. Anyway, here's what happens. So in the transport layer, first of all, in the application layer, whatever application you're using, let's say it was an email program, you generate an email, comes out of your brain into the keyboard, up into the application layer of the computer. Where's my mouse? The application layer contacts the transport layer inside your computer. The transport layer realizes, hey, this email message you just typed is too long. I need to segment that into multiple 1460 byte segments. And the segment sizes, by the way, can be variable. The first 2 or 3 might be 1416, and the fourth one or the final one may only be 20 or 30 bytes long. That's completely okay. Just like on our freeways, we've got different size cars, big cars and small cars. So each one of these segments now has to be addressed with port numbers, source and destination port numbers, and then one at a time, not both at the same time, but one at a time. Each one of these segments is handed down to the network layer, and the network layer then is responsible for routing and addressing those messages, and that's what I was going to talk about today. The routing and the addressing. The network layer determines the best path to take through the internet all the way to the end, the ultimate recipient, point Z we call it, not point A to point B, but point A to point Z, determines the best route to take, addresses that message appropriately, that packet appropriately, sends that down to the data link layer, and then the data link layer, that layer is responsible only for the physical connection between your computer and the next physical device. So the data link layer adds your MAC address, and then the MAC address of the gateway device you're attached to, or not even the gateway. The MAC address could be the MAC address of the wireless access point you're attached to, which is not necessarily your gateway. Does anybody in here have a mesh wireless access network at home where you've got multiple wireless access points throughout your house that are wireless, and then they talk to the Comcast gateway or the Xfinity gateway or whatever gateway you're using? So you may actually be communicating hardware-wise, physical-wise, to a wireless access point, not necessarily to your gateway yet. Eventually, the recipient computer, and now these are never right next door to each other, but the recipient computer will receive one or more of these frames, one at a time. I know this is a little strange looking, but at one at a time, the frame passes back to the network layer. The network layer looks at the source and destination address, determines if this packet is indeed for the recipient. This packet, it's possible. It is very possible for your computer or your device, even if this isn't a computer, let's say it's a router, to receive a packet which is not intended for this application layer. It's intended for a different computer. In that case, your computer is acting as a router and it basically recreates a new packet and sends it back down to the data link layer and sends it back out onto the network wherever it needs to go. So routers and special connecting devices and switches don't have a transport layer or an application layer because they're not receiving, their job is not to receive data into an application. Their job is to just transmit your data from one physical network to another physical network. But in the case of a sender and a receiver, this is point A and this is point Z. When I say point Z, that's somewhere which might be 1, 2, an X amount of hops. We don't know how many physical hops away. The recipient is. He's the ultimate receiver of the application data you're trying to send. The packets are handed to the transport layer. The transport layer says, okay, well, he assumes these packets are for him. He assumes these are packets. They were given to me, so I must assume they are for this computer. Let me look at the port number. Oh, it's port 25. This must be email traffic. So first of all, I will put all of these segments back together. And the way these segments are put back together, by the way, if you look back at the header, all the segments are numbered in a message. When you created an email over here in the sender, your transport layer, when it was breaking them all up, numbered them all. Just like you would if you were writing a book or if you were tearing pages out of a book or tearing up a message into smaller pieces. If you want to put all those pieces back together in the right order, you will number them. 1 of 25, 2 of 25, 3 of 25. That same thing is going on in the transport layers. Transport layer here on the recipient side, he reads those 1 of 25, 2 of 25, and puts things back in the correct order. It's also possible that sometimes your computer will receive a segment or a packet out of order, because not all packets go in the same, particularly if you're a very far distance away from the receiver. You may get some pieces of a message over satellite, some pieces of a message over a trans-Pacific or a transatlantic cable, a cable underneath the water, underneath the ocean. Did you guys know we still have cables under the ocean? That's still the fastest way to send network data from here to Asia and from here to Europe. Satellite's kind of slow. Let me look at my chat window here. Somebody's sending chats. So yeah, we still use, in fact, we have hundreds of transatlantic and transpacific cables. So the point is that the transport layer has to look at those sequence numbers and put them back in sequence. Ultimately, the completed message, the entire email, the entire web request or web page is put back into one block of information, which is given to the application layer program defined by the port number that was in the data. So if these segments that are coming in were all labeled as port 80 or port 25, you have within your computer a list when Windows is installed and when Mac OS is installed. You can actually go modify this list. It's called a MIME type list. It designates which default application you're supposed to use for a particular segment type. If the segment is numbered as port 80, you're supposed to use whatever your default program is, whatever you set it to be, Internet Explorer or Edge or Chrome. If it's an email packet designated by either port 25 or port 143 or 993, there's actually 5 popular email port numbers. Your computer has been told, usually by default or when you install the program, it's been told, look out for anything that's with these numbers. And that's the glue that ties the application layer to the transport layer. You've got a special file on your computer. It's just pretty much 2 columns. One's a bunch of port numbers, and then the column on the right is the application that's supposed to be receiving those segments, okay? So as I mentioned before, the transport layer is also responsible for session management. I mentioned this in yesterday's class. TCP being connection oriented, UDP being connectionless. And a TCP connection, and when we do get to the Wireshark assignment, which we'll start on those next week, okay? I want you to get through the test. One of the first Wireshark assignments I have you do is you install Wireshark. You fire up your favorite web browser, presumably that's Chrome, and you put in a filter to look for all traffic on port 80, destination port 80, which is the web port, and then you surf to your favorite web page, whatever that is, uh.edu, and the first 3 packets that you see in Wireshark should be a send packet, a synchronization packet, which is kind of like a ring and a ring packet that gets sent out onto the network. That's you're ringing somebody up. An acknowledgement packet that you get back from the server that you're trying to talk to. That's kind of like when you pick up the phone and go, hello. That's the acknowledgement packet. And then your computer sends back an acknowledgement that acknowledged the acknowledgement. So consider this like a telephone call. Your computer makes a telephone call. That's like the send packet, the synchronization packet going out. The recipient server responds with hello, and then you respond with, hi, I'm Jake. I want to start a conversation. And then from there, everything past that is just internet traffic or web traffic that gets passed back and forth. That's what happens in TCP. Here's some examples of addresses. So addressing, we have addresses at every single layer. And again, on the exam, I'm going to put a chart on there, and I'm going to ask you to fill that chart in, and I'm going to ask you to give me examples of protocols and actual example addresses. Don't get those two mixed up. So at the application layer, an example protocol, by the way, the example protocol would be HTTP, Hypertext Transport Protocol, or even HTML. That's also an application layer protocol, but it's not a transport protocol. An example address would be a web address, www.indiana.edu or uh.edu, or jake@uh.edu. That's an email address, but that's an application layer address. What's missing from this chart is the transport layer. Transport layer, an example address of the transport layer would be port 80, port 25, port 443. They're port numbers, okay? Not IP addresses, port numbers. And then at the network layer, layer 3, the dominant protocol is IP. That's pretty much the only one we use. We use IP version 4 and IP version 6, but still 97% of the world is using IP version 4. An example of that would be simply an IP address. You can look your own up. You go to whatismyip.com and put that in for that answer. That's an actual example. Data link layer, layer 2. That's the MAC address. Again, that's stood for Media Access Control. The common protocol that's there is Ethernet. Ethernet is a data link protocol. DOCSIS and DSL, you could put those down as data link protocols, but they're not really. Again, those are protocol suites. 802.11n, that is not a data link layer protocol. You might read in some notes that it's a data link layer protocol, but it's a specific marriage of a physical layer protocol, which is using the 2.4 or 5.0 gigahertz radio ranges, and a special data link protocol, which looks like Ethernet, to accomplish wireless communication. I'll accept it as an answer, as a correct answer on the test, but I would prefer, if you're asked this question, give me an example of a data link layer protocol. You should say Ethernet, okay? You can say DOCSIS and you can say DSL, but Ethernet is the dominant one. If I ask for an example address, that is the, Microsoft calls it the physical address, but that's the data link layer address. That number is hard-coded. When manufacturers, and I don't know if I mentioned this before in the previous data link chat, but when manufacturers of internet equipment or networking equipment or anything that needs to attach to a network want to put in an Ethernet port or a wireless radio antenna in their device, they have to allocate a unique hardware address. These addresses are allocated in blocks to hardware manufacturers, and then they dole them out how they see fit to their various devices. They're usually not duplicated, but they do get duplicated about every 10 years or so. a manufacturer will start reusing their data link layer addresses. Now, it's very, very unlikely that you will buy a device today and then 10 years from now buy another device. It's extremely unlikely they'll both have the same MAC address. And even if there were two devices with the same MAC address, it's very unlikely they're on the same LAN. MAC addresses are only used on LANs. So that MAC address that's right there, I could have that on my laptop and you could have that on your laptop. And as long as we're never talking on the same LAN, we won't confuse the equipment. But that's an example of the data link layer address. Now, physical layer, if I ask you for an example of a physical layer address, what should you put? And it's kind of confusing. You could put that, but that's not really a physical layer address. The physical layer, what defines a physical layer? What is the one defining factor of a physical layer that makes it different from all the other layers?
You actually touch it or see it.
You can touch it or see it or feel the effects of it. You can't see radio waves, but you can certainly feel the effects of those radio waves. But yeah, that's the point. So a physical address of numbers doesn't mean anything. What would be a better example of a physical address? How about room 122, Bauer College of Business or Melcher Hall? In other words, what I'm looking for in the exam is literally a physical address. Or port 23 in rack 5 in building 3. I'm literally looking for, you can write almost anything there on the test and it will be accepted. But I just want you to understand the difference between that numeric address there, which is a hard-coded number. It's actually hard-coded into the chips, but it can be changed. Some Ethernet cards let you change that. If it's a virtual machine that you've created, that number gets randomly generated. That's not a physical address. So please don't put that. Put port 2, port 3. Put I'm sitting in seat number 23, or I'm in room 122 of Melcher Hall, or I'm in classroom 138 or whatever, your favorite classroom that you're usually sitting in there in Melcher. Okay, so
That's for the physical layer, correct, sir?
yeah, for physical layer. Okay, so network layer functions in IP version 4, as I mentioned before, it's 32 bits, 32 ones and zeros. If you were to use a calculator, and this is where I recommend, if I do start, and I don't ask these questions on exam 2, I ask them on exam, I don't ask you to do any calculations on exam 1, but I do want you to understand for exam 1 that IP version 4 is 32 bits, 32 ones and zeros. We as humans convert those bits into bytes or into base 10. Bits are base 2. We count in base 10. So if you were to calculate that out, binary conversion, it would end up being a 129. Now, I used to teach people how to do binary calculation, but nobody does that anymore. What most people do, what even network managers do, is we just go look up a binary net mask calculator, or you can even ask Google. Here, let's do this. Translate binary 100. Is that 8 bits? One, 2, 3, 4, 5, 6, 7, 8. Yeah, 2 decimal. Let's see if Google's smart enough to do it. It is. So Google just translated that for us. So most of us use programs to do that translation for us. Hang on one second for me. Just need to tell somebody I was in the middle of a class, and please quit texting me. Okay, now I'm going to lose a couple people here. Hopefully not, but I might lose a couple people conceptually here. How are we doing on time, by the way? We're fine. Addressing. A portion of the IP address represents the network and the rest identifies the host. Now, the difference between a network and a host is any device on a network, and it gets a unique number. And then the network itself, which is identified by a number, represents one or more hosts, usually two or more hosts. You can think about this analogy-wise like an apartment complex. The apartment complex has a street address, 1234 Bel Air Street, and then each one of the apartments within that apartment complex has their own individual address. So if you think about that, like if you tried to send a letter to somebody at 1234 Bel Air, the post office may not know how to address that unless it's got an apartment number on it or a suite number on it. Usually they just take it to the manager's office, but they have to know where the manager's office is. So a network number refers to a grouping of hosts. You can't send traffic. You can't send data specifically to a network as the end user of the data. It can go through a network, but not to a network. So in IP version 4, we have two different ways of enumerating our networking. We have classful addressing and classless addressing, or CIDR notation. There's a notation called a subnet mask to more flexibly divide address space. So if you were to look up your IP address, in 99% of everybody's cases, if you go look up, you click down here on your network information, open your network and sharing center. Eventually you find this page. You'll get an IP version 4 address. Mine's 10.0.0.6. There's my gateway, 10.0.0.1. That's the IP address of the device that's going to send traffic for me onto the internet. This subnet mask right there, 255.255.255.0. I bet everybody in here has got that subnet mask. What that basically does, the way this works is, these are actually ones. All those 255s are really a bunch of ones, and that's a 0. What that means is anywhere, I basically overlay that subnet mask onto my IP address. Anywhere where there's a 0, that indicates that that IP address is local to me. So for example, if I sent a message out of my computer and the destination address was 10.0.0.7, with this subnet mask, that tells my packet that the device I'm talking to is on my local network. You can send it directly to 10.0.0.7 because it's physically attached to the same network you're on. If I needed to send some information to another computer like 129.7.1.3, none of those numbers match, because anywhere where I see a 255 or all ones, it masks off that part. It says, okay, well, none of these match. You understand what I'm saying when I say none of these match? Let me bring up. All that you do with a subnet mask is you basically overlay one over the other. So if your address is, or here, I'll use an example address that most of you are using, 192.168.1.35, okay? And your subnet mask is 255.255.255.0, or add also equals 11111111111.1111111.11111 or 00. 8 ones equals 255. 8 ones equals 255. It actually equals 256, but we started 0. And 0 decimal equals 0 binary. Do you agree that that equals that? That in decimal is that in binary. So I take my information and I take my number And let's pretend that we're trying to send traffic to 192.168.1.38. Excuse me, 192. So you overlay these, or let's just put them under each little chunk here. And we're going to talk a lot more about this next week because your guys are going to start doing subnet masking and subnet allocation. So with this information and all those ones, if I'm sending information to that IP address, that matches, that matches, that matches, that doesn't match, but that's okay because I'm on a network of all zeros. In other words, it's like a wild card. So I can take my packet, the data link layer will create a frame and it will literally send it out onto the local network. There's a command that I use a lot to see what computers, and this doesn't always work for all computers, but if you open up a command line, you can type in ARP -A, and I know you can do something similar on a Mac, and it will ARP space -A. This is called Address Resolution Protocol, and it will tell me there's the data link layer addresses, the physical addresses Microsoft calls them, and here's the IP addresses. This happens to be some, not all, but some of the devices on my local network. So if I'm at 10.0.0. whatever I said I was, 152 I think I'm at, and I needed to send a message to a computer that's on my local network, it's going to look up in this table the data link layer address, the MAC address, create a frame, and it's going to go directly there. But if I need to send that message to anywhere else, that net mask defines that. It says, well, I'm going to have to send that to the gateway. So everybody, when you're looking at your network information, everybody has a gateway address. If you don't have a gateway address, you can't send data out the door. You can only talk to other computers on your local network. So the four things, here are the four things. Your computer, everybody's computer, everybody's host needs four things to communicate on the internet, I should say. Okay, you need an IP address, and I'm talking about at layer 3. Okay, not at layer 4, layer 5. Of course, you need to know somebody's application layer address. You need their email address to communicate with them. You need their web address to communicate with them. But at layer 3, you need four things. You need your unique IP address. You need the IP address. You need a subnet mask, which defines the size of your local network. Then you need a gateway address, which is going to be basically the number of the device that's connected to the outside world and your local network. That's why we call it a gateway. It usually is a special purpose device, which has Wi-Fi built in, and it's got a Comcast cable coming in the back or a fiber cable coming in the back. It has two IP addresses. It's got a private address and a public address. And then you need one more thing. You don't need one more thing, but it's very helpful to have one more thing. You need to have the IP address of at least one DNS server. What is DNS? Have we talked about DNS yet? Or do you guys know what DNS is? Some of you know, if not all of you. It's not what I want. Where's the chat stuff? What's DNS? Anybody? Not just what it stands for, but what do we need DNS for? Does anybody know what we need DNS for? Domain name services, actually. Domain name services. That's really what it stands for.
Is that what translates your, kind of like what routes to whatever router has the actual URL?
Not really routes, but just all the DNS is it translates names to IP addresses. We as humans aren't very good with numbers. I mean, we remember telephone numbers, but it would be difficult for us to remember IP addresses. Back in the old days, before DNS, my email address is jake@129.7.1.7. I literally would give that out. Say, that's how you email me. You send a message to jake@129.7.1.7. Well, around the early 90s, with the invention of the World Wide Web, some companies got together and said, look, this is silly. Nobody's going to remember all these different numbers. Let's find a way to name these numbers, and that's where DNS came from. And you register domain names with different registrars, and usually you associate your domain name with one or more IP addresses. So DNS is so that our application layer can simply use jake@uh.edu. And you can do this as an experiment, just to see how this works. Minimize that for a second. Let's use the ping command. Ping www.uh.edu. Let's see what we get when we do that. Now, what happened just then is that my computer created a special message that went to the DNS server, which you have to know the IP of. It says, hey, would you please look up for me what www.uh.edu resolves to, because the ping command is a layer 3 network command. It creates an IP packet, and actually creates a segment too, a special segment, but it sends this message out on the network specifically with an IP address, not an application layer name. Layer 3 doesn't understand application layer addresses. If a layer 3 layer received a request with a domain name in it, it wouldn't know what to do with it. It has to be an IP address. So 129.7.97.54, remember that, 97.54. If I want to go to uofh.edu, I can type in www.uh.edu, hit enter, and here I go. Or you can also type in 129.7. What was that number, 97.54? And you'll also get uh.edu. You'll get it faster. Also, and this is what this is the true thing, the actual thing that's coming out of your computer is, in this case, http://129.7.97.54:80. So what have I just defined here? That's the actual URL. That's really what's coming out of your browser. You don't type that stuff in because your browser's sticking it in for you. Your DNS lookup is giving you the IP address for you, but you're defining a protocol, an application layer protocol. You're defining a transport layer port number there, and you are defining an IP network layer address. So I'm defining all 3 addresses here. And of course, it'll give me the same data. Retranslates it into something else, but essentially it's the same data. That's how those things are interrelated. So if you ever want to just quickly look up somebody's IP address, an easy way to do it is just open a command line and type in ping, whatever you want to look up, google.com, for example. That is google.com's IP address, their public IP address, at least for today. It might be different tomorrow, might be different an hour from now, it might be different for you because you live in a different part of the city or a different part of the country, but these names resolve to multiple addresses, but for a big company. Okay, so back to the PowerPoint. I want you to understand, for purposes of the subnet masking, let me go back to this for a second. A subnet mask is always some number of 1s to the left and some number of 0s to the right. You'll never see a subnet mask that looks like this. Okay, it's always going to be some number of 1s to the left and some number of 0s to the right, being 32 bits worth. In other words, 32 characters. That's probably not 32 characters, but I'm not going to bother to count those. And that gets translated into, in the case of using classful addressing, it's translated into 255.255. something something. In fact, you can go Google for it and look up. And again, this is what we typically do. We do not, as network managers, figure this stuff out in our heads, although some of us do because we've been doing it a long time. You can Google for, let's see, binary to decimal net mask chart. You can, and let's search for images, okay? We can find a bunch of them here. There's a fairly decent one there. Okay, so this photo or this image, what this is showing me is some of a net mask or some of an internet connection. Now, most of you are operating on an internal network, so it's a /24, or your subnet mask is 255.255.255.0, one subnet. There can be 256 hosts because what's 2 to the 8th power? If there's 8 zeros here, 2 to the 8th power is 256. Really can only be 254, by the way, because we lose the top and bottom number. But in classless notation, CIDR notation, we just simply state the number. We don't use a subnet mask. We just state the number of ones after a slash. Go away. Now, some of you might be on a larger network. As a matter of fact, if you're on a wireless network at U of H, you're actually operating with a net mask of 255.255.0.0. And there's 65,536 possible hosts on that LAN. And that's because it's a wireless network. It's a lot bigger. The slash notation is /16. So when we're writing out and defining network addresses, your network address, when I talk about those pieces of information you need, 129.7.1.7, let's just pretend I'm on the UH server. You either specify a net mask or you simply write the address like this, /24. Those two things mean the same thing. That IP address with that net mask or just that, it means the same thing. Number of ones in the subnet mask. That's all that means. It's a shortcut. It's an easier way to write the network number. So in this case, if I were to ask you the question with CIDR notation, what items do you need? You need an IP address, which is that. Then you need the subnet mask, or I'll put that on a different line. So you either need a /24 or a 255.255.255.0. You need a gateway address and a DNS server. Now, most of you just have one DNS server, but again, when you're at U of H, when we finally do get back there, I'd like everybody to do this. Go check out what your details are of your local area connection, and you'll notice that you probably have 3, 4, or 5 DNS servers. I've only got one here, and in 99% of the cases for most of you right now, your gateway, your DHCP, and your DNS server are all three the same thing. And 99% of the cases, and that's because, again, you're talking to a special purpose device that either Xfinity or Comcast or AT&T is providing to you, and it's doing all of these things for you. It's providing DHCP, handing out addresses on the local network. It's providing the gateway physical connectivity, and it's also doing DNS lookups for you on the internet on your behalf. And rather than your computer having to do the DNS lookups, your gateway is doing the DNS lookups and sending the responses down to you. At U of H on the wireless network, that default gateway will be different from the DHCP server, and you'll end up having 3 or 4 or 5 DNS servers. Also, you don't have to use the local DNS server. Some people choose to use, they go into their properties for their connections, and they change this, and this is why this is optional. Maybe you don't like the DNS servers. Maybe they're slow, because DNS can be slow. So you might want to use some of the popular public DNSs like 1.1.1.1. Or actually more often people use Google's 8.8.8.8, public DNS. Or if you're on Comcast, you might want to use 75.75.75.75. That's their DNS number, although it's not public. Okay, so if I ask you on a test, what 4 things do you need? You need an IP address, some sort of net mask notation, whether it's regular 255 subnet notation or the slash notation. We also call it slash notation. You need a gateway address of something else to send your messages on when they need to go out of your local area network. And then you need an IP address of at least one DNS server, but you don't really need that. You need that so that you don't have to look up IP addresses manually, or because we don't know anybody's IP addresses. And also IP addresses change periodically. You change internet providers, your IP address is going to change. If you have multiple web servers, the IP address is going to change. It's dynamic. Okay. So DHCP, does everybody know what DHCP is? Most workstations, not servers, but most workstations on the internet are using DHCP to receive a temporary IP address. Back in the old days with networking, we used to have to go around to everybody's workstation and hard code in, we call it hard coding, and give everybody a unique IP address. But some smart guy came up with a protocol which will hand out addresses from a table. Excuse me, it'll lease an address to you. It's kind of like leasing you a telephone number or a telephone. So let's say you show up at work to go do your work, and there's somebody standing at the door, and you say, hey, I need a telephone so I can start calling customers or whatever, and they hand you a cell phone. Say, here you go. It's something like that. So when you first turn your computer on, your computer sends out a special broadcast message to like the entire network. It says, I am a new computer on the network. I need an IP address. Who has, are there any DHCP servers out there? Presumably there's one and only one DHCP server on your network segment. If there's more than one, that causes a problem. One on your network segment, it picks up this response. It says, okay, I recognize that your MAC address is, and it looks up your MAC address. You do that, oh, not IP address, IP config. I'm a Linux guy, so I type in these physical addresses. It looks up your MAC address and says, okay, I'm going to assign you an IP address out of a range of addresses I've been pre-programmed with, and I'm going to associate your IP address with your MAC address. And I'm going to lease it to you for X amount of time. In fact, that information is in here. If I scroll up, you can see when your lease was obtained and when it expires. Typically, that's 1 to 2 days. Sometimes it's as long as a week. It's rarely ever more than a week. It might be if you're on a very dynamic network, like you're at Starbucks, the lease might be 1 hour or 2 hours. The concept of DHCP is not just for your convenience, not just so that we don't have to pre-number computers based on IP. That would be very difficult because everybody moves their computers around now, and you're jumping on different LANs. You're no longer connected to one LAN. It's not just for convenience, it's also for multi-tenancy. So Starbucks, for example, they'll set up a little network and they'll set up a Class C, which can handle 250 something connections, although they don't usually make the range that big because of course they have a bunch of equipment. They may make a DHCP range of no more than 50 addresses. Now, will they have more than 50 customers in one day? You bet, it's a Starbucks. What they do is they'll change the lease time down to 1 hour because it's presumed you're not going to be there longer than 1 hour. Unless you're like some of these students I've seen that sit in a Starbucks for multiple hours. Anybody live at Starbucks here? I know some of you probably do. You're there at Starbucks all the time. Or maybe you were when you were in high school, because it was not your home and they had pretty decent internet service. So occasionally you would have to renew your IP. You try surfing and it would hesitate, and then you get another number. So organizations that have customers coming in and out, like hotels, for example, or Starbucks, they'll lease you an IP address just for a short period of time, and then they put it back in their pool. It's called an address pool. And then you have to request it again, or somebody else can request it, and they'll get that IP address to use temporarily. Excuse me. Stands for Dynamic Host Configuration Protocol. It's not that important that you remember what this stands for. Just understand what DHCP does. It's a huge time saver. It's a very powerful protocol. It doesn't really fit. You know, you can't really say it's layer 3 or layer 4 or layer 5 protocol. It doesn't fit well into that model. But it's different. Understand that it is different from DNS. DNS is specifically to look up IP addresses to names. DHCP is to give your computer an IP address so that it can operate on a network. And then finally, the thing I showed you earlier, that ARP, your computer is also resolving MAC addresses, not Mac OS. I'm not talking about Apple, but media access control addresses. It is associating those with IP addresses. So that's on your local network. Everybody has a MAC address on a local network, and they're given one or more. You might have multiple IP addresses. In fact, most servers have multiple IP addresses. Most workstations actually do too, because everybody gets the local IP address called the loopback address of 129.7.0.0.1. If I were to type in route space route print without the /, this will tell me a little bit more information too. ARP-A, route, IP config. These are all great little utility programs that come with most OSs. So my computer actually has an address of 127.0.0.1. That's called the loopback address. Here's the net mesh. Notice how it's all 255s? If you're on a network where the net mesh is all 255s, what does that mean? That means that's not a network. That's just you. If you're on a network which is all zeros, that means that's the outside world. So everybody has this first entry here at the top of that table that I just created, route print, by the way. That defines where the world can be accessed. In other words, what am I using? Gateway. If I have some data that needs to go to something that I don't know about, that my network doesn't know about, it's some totally foreign address, whatever it is, send it to the gateway. In other words, I need to send a letter to somebody who's not in my apartment complex, so I can't just go knock on their door and give it to them. I got to go downstairs and put that in the mailbox to go out to wherever it needs to go to. And let the mailman worry about it. It's addressed up here at the application layer, but we don't have to write on that letter, mailman, please take this to your local post office, and then take that to the central post office in downtown Houston. We don't need to do that kind of addressing and routing. Okay, so we got resolution is the term that we use, by the way, to look up one layer protocol and see what the next layer down actual address is. So address resolution between layer 5 and 3, and actually skips layer 4. Between layer 5 and 3 is called DNS. And resolution at the MAC layer, associating physical MAC addresses with IP address, is called ARP resolution. Now DNS, just keep in mind that DNS is a distributed situation. DNS is basically the directory for the internet. It's like the phone directory for the internet. But the internet is huge, And there isn't just one phone directory in the world. There are multiple phone directories, and they have multiple duplicate entries in them. Your computer is given a partial phone book from your upstream provider. And every time that you try to go somewhere new that your upstream provider doesn't know the IP address for, it has to make a request to its upstream provider and its upstream DNS server. Within each country, there are root servers. If we were to look up, let's go look up DNS root servers. What are the root servers? There they are. There's only 13 of them in the whole world. Those are the root servers. They're very busy, but all they're doing is they're answering requests from the next layer down. This is a hierarchy. This is how this works. So let's say I want to go to a very popular website, espn.com or uh.edu or something like that. It's presumable that the server I'm communicating with, or I shouldn't say the server, the devices I'm communicating with, the internet provider I'm communicating with, they already have that information cached in their local tables, especially if you're using a Houston provider and you're going to uh.edu. That's definitely in their network cache. But if they didn't have it in their network cache, they would make a request up to their upstream provider's server, and it might ultimately go all the way back, excuse me, what's on my phone there, all the way back to the root servers, and it would have to look up where uh.edu actually lives. So, and we're going to talk more about DNS at a later time, but just keep in mind that DNS is distributed. It's really DDNS is really what it is. It's pieces of the phone book. Pieces of the internet phone book are split up all over the world, and some of them have multiple entries. Now, once let's say you look up an obscure site, and as a matter of fact, you can do this as an experiment. Go to a website that you go to all the time. Something you went to earlier today, like google.com or something like that. It'll come up fast. And then go Google for some obscure website, like a website in another country. You know, go look up like the country of Finland, a bar or a pub or something in the UK, or something that's obscure. You'll notice when you go to look it up and you find it in Google and you click on that link to go to their website if they have one, you'll notice it'll take several seconds longer before it even starts loading that web page. And it's not because it's far away, most likely because a lot of this DNS resolution is having to figure out, okay, where is this, lionspub.co.uk? What is its IP address? Well, I've got to go up 3, 4, 5, 6, 7 levels to finally get to the root servers that are in the UK that will tell me. Or go back to the registrar of this domain name. What are your IP addresses? So it might take a little while, but once your computer learns it, your computer puts that information in a little cache table. And so the next time you go there, if you refresh the page, it'll come back much faster. It's still pulling the data down, but it's not doing that lookup again because it already looked that up. Now I'll point out one other thing here. How are we doing on time? Okay. You've got a local table, which you can modify. In fact, we do this in 4397. This is true for Mac and this is true for Windows. And this is true for any host on the internet. And this is before DNS. Before we had DNS, we actually hard-coded information into a table called hosts. Now it's in different places on different computers and in different OS types, I should say. In Windows 10, it's under Windows, System 32, drivers, and I don't know why it is. It should be off the root directory, drivers, etc, which stands for etc. And there's a file there called hosts. Open it up. Don't edit it, but open it up. Take a look at it. Open with let's just open it with, I'll open it with Notepad. There's the hosts file. Now, anywhere where you see a pound sign, that's simply a comment. But if I wanted to, and a lot of people do this when they're experimenting or creating new websites, I could hard code in, like for example, that the EI Lab server is at 192.138.194.45. Let's say I wanted to give it a shortcut name. I just call it eilab.com. Now, there probably is a real eilab.com in the world. But if I were to put that information into that file and save it, I'm not sure if I think I may need to, yeah, I need to run that as the administrator, excuse me. Need to do this one slightly different way. I need to run this program as an administrator, or it won't let me save that file. Open. Oh, sorry, C colon. Let's see if I can just find it really quick. Windows. System 32. So I'd like you guys to do this. It's just an experiment. Just be careful. Don't mess up the file too bad. All documents, hosts. You could put in your own DNS information because your computer always looks in the host file first. 192.138.194.45 eilab. I'll just call it eilab.jake. I just made up a brand new top level domain. Bet you didn't know you could do that. I made one up. Let's save that. Now let's see what happens if I open a browser and I try to go to eilab.jake. It's actually going to, and the reason that that's doing that is because that's the first page that you see when you try to go to the EI Lab from the outside world. Pretty neat, huh? So you can hard code anything you wanted to in this file, any IP address, and give yourself any name. As a matter of fact, if you really wanted to freak somebody out, you could set up your own web server, like on your local network. So let's say your computer's running at 10.0.0.25 internally on your network. You can freak your siblings out with this. Download a web server like Apache, or there's a lot of free web servers. Create a web page, and just make it a very simple web page, and call it IBM.com or Google.com. You really want to have fun with somebody. Save that, and then get somebody to sit down to your computer and say, hey man, could you go to Google? I think I'm having a problem. I'll type in google.com, and it'll bring up that server page that you created. It'll only work on this computer. You have to edit this host file on the computer they're using, but you can do some interesting things. And I'm not saying that you should, mess up your local computers, but some companies do this so that they can prevent their customers, not their customers, but their employees from going to certain websites they don't want them to go to. So if they didn't, want them to go to certain websites, they would essentially redirect the traffic to an internal server, and that IP address there would go to an internal server, which would bring up a web page that says, we were watching you, don't do that, or whatever. I'm not going to save that information. Well, actually, I'm going to save that to empty it back out. Okay. So the network layer is responsible for routing and addressing messages. We've talked about addressing. Now, what is routing? That involves that that network table. And for it involves the the subnet mask. And all you really need to know from this, because I don't want to get too complicated with routing, but in a network, your subnet mask and your IP address figure out what's the best route to send information, but it really only figures out, in this case, let's say A needs to send a message to G. A is not connected to G, but A is connected to B and D and E and F and C and then G. So what will happen is your computer, if it does have multiple connections to somewhere, it might send out some test packets to see what's fastest. Now, it's unlikely. Most of you don't have multiple routes, but some computers do. You have 2 network cards or 3 network cards, especially if you're a server, 2, 3, 4, 5 network cards in your server. That network server will send out messages to see what the shortest path is or the appropriate path to get information from point A to point G in this example. Now, like I said, for most of you, you just have the one route from A to B or A to D. So your computer's not really doing much routing other than it's going, well, this packet is for something I'm not physically connected to. So I'm going to send it to B, and B better be connected to something else, and he'll figure out how to send it to his next hop. So we're going to talk more about routing after you guys take exam 2, but just understand the network layer, its responsibility is addressing those messages and then figuring out, is this packet for a computer on my local network, in which case I would look up the information in that ARP table, or is it intended for the gateway device because it has to go to the outside world? So we can skip this stuff for right now. Let me just briefly mention this, the difference between centralized and decentralized routing. Centralized routing is where the decisions are made by one computer, or in the case of where I simply hard-coded that DNS information in, I basically could have done that with routing as well. If I had 2 or more routing network cards in my computer, I could have said, hey, all of U of H, you should send the traffic out network card A, and all of the rest of the world send the network traffic out network card B. Usually most networks are decentralized. Decentralized routing, each node is independent of another. Each of the servers that are receiving the information between you and the ultimate recipient is deciding how best to send that message. That's what the internet is using. There's many, many overlapping connections on the internet. So your packets that you're sending out from your computer, they're taking a different path every time. Just like between here and where I live in U of H, there's a dozen different routes I could take. I don't decide when I leave my house because I don't know what the and that's the point of decentralized routing. I don't know what the conditions are out there, but I do know, well, I got to drive down my driveway because I've only got one driveway out of my house. And then at that point, I start making decisions based on traffic, based on conditions, based on weather. I make decisions in a decentralized fashion. I don't usually, and maybe some of you do this, you go look up the route from here to U of H on MapQuest or Waze, and you follow that specific route. Fortunately, these apps like Waze, at least Waze, I don't know about MapQuest. Anybody use Waze in here instead of MapQuest? I use Waze much more than MapQuest now because it is more like decentralized routing. If it notices, hey, the traffic's getting really bad on that route that I told you to go on, I told you to go 610, but whoa, the traffic's getting really bad. Or there was a car accident, or there's police officers pulling people over. It might tell me immediately, hey, don't get on 610, go down alternate 90 and get on Holmes Road instead, or go some other way. That's dynamic routing. It's slower to do anything dynamically. It's a little bit slower. Static is faster. If I hard code everything, if I hard code IP addresses, if I hard code routes, everything's faster. What I want you to remember from this statement I'm making right now is that doing anything statically makes your transmissions faster. If I don't have to look up what uh.edu resolves to, if I don't have to if I know the route from point A to point Z, I can hard code that in. Things are going to operate faster, but nobody does that. At least data that we're sending out on the internet, because the internet's changing constantly. Conditions change constantly, just like when you're using Waze to get from here to U of H or here to San Antonio or here to wherever you're going to go. Maybe San Antonio is not a good choice, but an area away from you that has multiple potential good routes to get there. Conditions change, just like on the internet, conditions change all the time. So although dynamic routing and dynamic addressing takes a little bit more time, it can make your internet traffic go 3 to 5% slower, but it's necessary because of changing conditions. I'm not going to ask you to know what these different routing protocols are. We're not going to worry about RIP and OSPF right now. We might learn those a little bit later after exam 1. Let's see. How are we doing? Let me just briefly mention really quick. I already talked about this. These are the things that your computer needs. We already talked about this, those 4 items. In terms of broadcasting of messages, unicast versus broadcast versus multicast. Most communication on the internet is unicast communication. That's not unidirectional. It's unicast. In other words, your computer makes a connection with one other computer on the internet in the world, and you guys are having a one-to-one conversation. Might be pseudo-conversational, might be actually conversational. One-to-one. As far as you're concerned, you're talking to a server, and as far as a server is concerned, it's talking to you at any one point in time. Yes, it's talking to 1,000 other people, but at 1 microsecond of time, it's talking to just you, sending a packet or a frame or a segment just to you. That's called unicast. In the case of emailing, anything that's TCP is usually unicast. In the case of broadcast, that means one device is communicating with multiple devices on the network. It sends out a packet that doesn't have a particular IP address, or maybe it has an IP address of all zeros or 255. Like in the case of DHCP, all the computers at layer 3 can pick up that message and look at it, just like broadcast TV. In the case of broadcast television, the broadcaster doesn't know who's watching their signals, but it's more efficient in a lot of cases to send out certain types of communication that way. Like video and audio communication, streaming communication uses broadcast, or actually not usually broadcast, it uses something called multicast. Broadcasting doesn't work that well outside of LANs. We don't typically broadcast traffic on the internet because broadcasting is bad. It takes up bandwidth. If you just, broadcasting is like there's a guy standing on the street just screaming information out. Only 2 or 3 people anywhere near him might care about what that information is, but everybody hears it. Like a billboard. Anybody drive down the freeway and you see a billboard? Catches your eye? Advertising, a particular type of whiskey or whatever. Maybe it has nothing to do with you and you don't give a crap, but you still saw it. They're trying to appeal to 1 or 2 people driving down the road every couple of hours. That's a broadcast message, but it's a cheap way and easy way to do something. Multicasting is very similar to broadcasting. What we are doing right now is a multicast network, video conferencing. With Zoom video conferencing, when you attach to Zoom, your computer is actually getting a special IP address. I have an IP address, and I'm sending out 1 packet of information, or actually 24 packets per second, basically. But I'm not sending out 1 data stream to every single person that's on this network. I'm sending out 1 data stream from me to Zoom, and then you're communicating with Zoom on a multicast network, which is like a temporary LAN, a temporary internet connection, where Zoom can send out 1 copy of the data, and several of you can see that 1 copy of the data. It's kind of like broadcast, but it's more like there's a speaker in a particular room. Let's say, has anybody ever been to a seminar or a convention? And the conventions, they have the big meeting, the breakfast meeting in the morning, and then eventually people break off and they go into smaller groups and they sign up for different seminars and different classes. It's kind of like that. You decide, I want to go learn about marketing or whatever. So I'm going to go to the marketing seminar, which is in room 123. So you go over to that room, and there's a guy talking in there, talking about selling and marketing, whatever the product is you're going to the convention for. Only the people in that room, only the people that have made the choice to enter that room, enter that network, are going to hear the traffic. Everybody else in the hallway or people in other rooms aren't going to hear that traffic. In other words, it's a better use of broadcasting, because not everybody on the network, not everybody on that LAN is going to get that information. So for the purposes of the test, I just want you to understand the difference between unicast, broadcast, and multicast. Unicast, two computers talking to each other. It's efficient when there's only two computers in the world, but if I needed to talk to a dozen different computers and send the same message, I'm sending out a dozen different data streams using unicast. When you guys send an email, by the way, think about this. When you send an email out to 50 people, your computer is literally generating 50 email messages. It might not save 50 copies of it, but your computer is sending out 50 copies of the same email. That's very inefficient to do that, and it takes a lot longer. It'd be better if you could send out one copy of that email and it goes to multiple people, as in the case of a news group or a special user group, where you send one message to that user group and it posts in that one newsroom or that one Facebook page, and then people go and they read it if they belong to that grouping. That's more like multicast. Okay. We're pretty much done here. I do want you to know the difference between these different devices. A host computer is basically any device on a LAN. Could be a server, could be a workstation. These other devices, gateways and routers, these are special purpose devices that move the traffic along on a LAN. They don't have layer 4 and layer 5. A switch doesn't even have layer 3. A network switch, which is a physical device that you connect workstations to, is layer 1 and 2, and that's it. It doesn't need a layer 3. Routers need layer 1, 2, and 3, but they don't need a 4 and 5 because they're not running applications. They're just a go-between. They're the doorman standing at the door to a club. They're going to let you in the door or let you out the door, but they're not the performers. They're not the ones on stage. You know, they're not the comedian. They're not the bartender delivering the drinks. They're just controlling traffic in and out. Okay? So I'll send out, well, actually in my notes on the test, on the exam. Now, if you go to, let's see, how am I doing on time? Probably out of time here. Yeah, I need to get ready for the next class. But if you if you go to the course content page, I have exam 1 study notes already there. Yes, they're from a previous semester, but they are more or less going to be the same thing. I might change a couple of things, but if I do change anything on here, I'll send you out an email and let you know what I changed. Like probably I'm going to take a couple of things off. Best way to study for my first test is read through the content here, copy and paste each one of these items into a different, like a WordPad document, answer those questions, type out the answers into that WordPad document, save that document, then go take the test. Open up that document and use it while you're taking the test. Test rules are basically pretty open. I say 2.5 hours. I'm actually going to change that to 3 hours. Okay, so I'll give you 3 hours to take the test. You can use the internet, you can use your notes, you can use Google, you can use whatever you want while you're taking the test. You just can't use each other. Okay, so that's why I say study for the test, but use whatever tools you want to during the test. Any questions about the test? I'll probably make it available tomorrow by 9, and I'll probably make it available through Monday at midnight. So read these notes first on the layout and how the test is to be delivered to you. It's going to be on Blackboard. If you have any questions, send me an email. Okay, I'll see you guys online on Zoom on Monday. Bye-bye.
Hi, when should we go over the Mac VPN?
Oh, yeah, I ran out of time, Nicole. I'm sorry.
Oh, it's okay.
Well, before we do that, I think probably it's not a problem with the Mac. It's a problem with how I've defined the users on the
Okay.
domain control. So let me fix that. Let me figure that part out first. And then if it's still a problem on Mac, then I might send you a message and see if we can walk it through. Okay. So let's not
Okay.
worry about it for right now.
Perfect. Thank you.
All right. See y'all later.